Hey, so welcome everyone to the Physics Colloquium series. We are very proud to have our one of our own here, one of our most recent additions to the department. The other one sitting right here, Aaron, who joined us in 2025, actually this year, right? So, okay, so welcome, Aaron. Aaron is a condensed matter theorist. He did his undergrad and his PhD at Cornell. And then moved on to do a postdoc at Ohio State University with Brian Skinner. And I'm not sure if there or already before you dabbled into hydrodynamics.
Already in my, and then end of my PhD.
Yeah. Already end of the PhD, yeah. So that became a very hot topic in some of the 2D materials communities and like condensed matter overall, where you need specific, he'll talk about it, like conditions where, you can get hydrodynamic properties of electron flow. So this is not about, it's not about water flow as you may think. You will hear about how nowadays you can see manifestations of this in condensed matter systems. Yeah, without further ado, Aaron, the floor is yours.
Yes, well, thank you very much. Oh. Let me dim the lights. Hopefully that's a little bit better. But yeah, thanks a lot for having me. I guess I had to make the long trip across the street to get over here. But yeah, so I wanted to tell you, as the title suggests, about two characters, right? The first one, as Matthias already pointed out, is about this hydrodynamic flow in electrons, which has been pretty exciting, especially in the 2D materials community of say, the past decade. But there's also a second interesting character that we were playing around with, known as current noise. And the mixing of these two properties or two phenomena leads to a lot of confusing, paradoxical, and exciting things, which I hope to tell you about. Good. So, is this working? Yeah, there we go. So I guess, as always, just feel free to interrupt me at any time if you have any questions. But before I begin, I'd like to go ahead and thank my collaborators. So the real heroes of all of this is Philip Kim and his group over at Harvard, Jonah and Artem, who have since moved on to bigger and better things. They were the ones who were studying experimentally some of these devices, and they saw a bunch of strange phenomena, and they basically bothered me and Brian to think about this a lot, and led to a series of nice works. There's also a number of kind of more like reviews and more popular writings if you're interested. But anyways, I wanted to begin just all the way back to talk about what is electron transport? How do we think about it? The way I like to describe it is it's essentially a mystery. You're trying to be a detective and understand what's happening, right? So what's going on? You have here, right? You apply some voltage. This leads to some current, right? You measure the relationship between these two, and that's called the resistance, which you can see the effect of. But under the hood, microscopically, the job of somebody who is doing a transport experiment is to say, what exactly is causing this resistance? Fundamentally, why does that resistance exist, right? Who is torturing my poor current? So, of course, this field goes back at least 100 years. We've been measuring electric currents for a long, long time. And it wasn't until around the 1900s, so this is the era when kinetic theory of gases was taking off, the beginnings of quantum mechanics as well. And so Drude basically said, let's just take this kinetic theory of gases and try to imagine, maybe in a metal, what we have is an electron flowing from left to right, and it's flying through under the influence of an electric field. And what causes resistance, he said, is the fact that there's a bunch of impurity scattering centers in my material, and anytime the electron hits one of these scattering centers, it loses all its momentum. So that's where it loses energy. That's what gives rise to resistance. You write down some differential equation, right? The Drude model. You solve it. You get J equals sigma E, which is just our usual formulation of Ohm's law. And the important point that Drude pointed out was that this sigma you can calculate in terms of microscopic parameters, where this gamma is this momentum relaxation rate, or the rate at which the electron scatters and hits the impurity. Okay, so even today, most of our transport experiments are interpreted through the lens of the Drude model. But there are other regimes of transport you can talk about and think about. So fast forward about 60 years, you can imagine what happens if I make my samples much, much cleaner, right? I start cleaning up all these impurities, removing them out of my sample, right? So in that case, now you actually end up changing the order of the length scale. So in this problem, you have the impurity scattering length being shorter than the other scattering lengths in the problem. Now, because now you have no more impurities, the boundary is the shortest length in the problem, or the size of the sample. So kind of semi-classically, you can kind of think of the electron primarily bouncing off the walls of the sample instead of impurities. You do the quantum mechanics of this problem, and what you find is this famous Landauer-Charvin result. So now you no longer have a notion of conductivity, but you have a conductance. So this conductance is independent of the length of the sample, and then you get this famous quantum unit of conductance, E squared over H. The conductance is going to be some multiple of this. Okay, so broadly speaking, more or less, most of our transport theory rests on kind of these two models, or these two pillars. You fast forward another 60 years or so, and in the 2010s, people started observing experimentally a third new regime of transport. This is what we call hydrodynamic transport. And so here, right, this is when electron impurity scattering length is shortest. This is when the sample size is the shortest, right? But you can imagine now turning on electron-electron interactions strong enough so that the electron-electron scattering length is the shortest length of the problem. And, well, okay, so first, this picture is going to be different from these two because this is an interacting picture versus these two, which are non-interacting. And the second thing to note about this problem, and the important part, is that as opposed to the collision processes in the first two, this collision process of electron-electron scattering conserves momentum in the electron system, right? And this conservation of momentum is very, very important. If you recall back to, say, around 1930s, there's this very famous Peierls argument that says that in order to have any resistance, the scattering mechanism must break translation symmetry, must relax momentum. Okay, so qualitatively, the transport in this device, this kind of system, will be different. And we actually know how to think about systems like this, right? If you think about water molecules, air molecules, fluids, the classical fluids and gases, well, that's kind of the typical setting in which we apply kinetic theory and its variants. We write down a hydrodynamic equation of motion, or Navier-Stokes equation of motion, right? So just like we do in water and air, in this regime where you have electron-electron scattering and momentum-conserving scattering, you can write down a Navier-Stokes equation, right? So if you compare this with Ohm's law, the main new features are this nonlinear convection term, which for the purposes of this talk, I'll just ignore nonlinearity. Mostly for the experts, Reynolds numbers tend to be low in these systems, otherwise you start blowing up your device. There have been recent experiments where they do blow up their device and see shock waves and things, so that's pretty interesting, but I'll just ignore it for now. And then the other new feature that we have is viscosity. So viscosity, you should think of as, when you pour honey out of your jar, it's very sticky, it's very viscous. It has high viscosity versus water, which is low viscosity. So that's this term here coming in with the grad squared, and then you have essentially this momentum relaxation term just as before. This is just because we can't make a device so clean we remove all the impurities, so there's usually some remnant of this left behind. Okay, so just as a comment on this, right, this procedure of writing down this Navier-Stokes equation is essentially some long wavelength effective expansion of the equation of motion when you have conserved momentum. So this kind of description is very, very widely general, everywhere from plasma physics to water flows all the way down to these small scales. when you talk about electron fluid, it works the exact same way because of this wide kind of universal description, Taylor series expansion description. Okay. So I noted in the previous slide, well, hydrodynamics is super old, right? We've known about Navier-Stokes since at least the 1800s, and it was even proposed in electron systems in 1960s by Gurgy. What took so long since the discovery of the Drude model to now to actually see this in experiment? The main problem is disorder in materials. So normally we think of copper as a good metal, gold is a good metal, right? But it actually turns out these objects are actually not clean enough. So I want to emphasize that the discovery of this hydrodynamic regime is really a heroic effort on the experimentalist part to make very, very clean samples. So if you look here, so this is 10 years ago in 2011, they used to be putting devices on silicon dioxide. Turns out silicon dioxide is really bad, graphene on top of silicon dioxide. Turns out that's not so good because silicon dioxide has a lot of charge trapping centers. So here's a map of the local electric potential, and you see all these charge puddlings. That's essentially giving rise to disorder. Then they started putting this on something else called hexagonal boron nitride, or HBN. It's almost invisible by comparison. This was back in 2011, right? People have been able to make even better samples now, right? I should comment that this precise reason is probably why I'm not an experimentalist. I used to actually grow graphene, right? And so one of the ways that you wanted to get ultra-pure graphene is like, let's just not put it on a substrate at all. Let's just float it over a hole, right? So you don't have any substrate effects. Of course, putting an atomic layer of carbon over a hole on micrometer size is generally a dangerous procedure because they can tend to tear. So because of my frustrations with that, I'm no longer doing that anymore. Anyways, so just some numbers, right? So for typical metal like copper or gold or something like that, the impurity scattering rate gamma is in the order of 100 terahertz. That's considered a good, clean metal, right? But if I look at the scale of graphene, the electron-electron interactions, which we normally say are strong, that's only on the order of 1 to 10 terahertz. So even for these metals, right, they're kind of way outside this hydrodynamic regime. If you start making these ultra-clean graphene devices, you get gammas on the order of 500 gigahertz. So you start crossing over into the regime where you can actually see hydrodynamics. So this is a pretty heroic effort. For the experts, there's also this, impurity is not the only thing you need to remove. You need to remove the phonons. So there's a temperature window in which you can look for this effect. Long story short, we're barely able to make devices so good that we can reach this regime now. Okay, so experimental details aside, let's just go back to the theory and think about, okay, let's say I have a hydrodynamic device. What does that buy me? What changes? Okay, so the first thing we do is, okay, well, the main thing is that the equation of motion changes, right? We now have this additional viscosity term, and we can go ahead and solve for the velocity profiles. I note that there's a new length scale that you add into the problem called the Gurgy length lambda, which is just the ratio of viscosity to gamma. And so I'll describe what that means in a second. But it's okay, so I just solve this in some rectangular geometries. So in the ohmic device, you get this flat rectangular flow profile, right, as you always see. But then when you have viscosity in the system, right, this changes the flow profile from a flat rectangle to a parabola. Right, and this, if you're familiar with fluid mechanics, this is often what's called Poisson flow. Okay, and then if you tune this lambda, you can go between these two limits from this rectangular float from this ohmic flow, and this lambda is more or less the range of this non-local effect, so how much curvature you have in this this flow profile. Okay, so that's kind of if you're familiar with fluid mechanics, this is probably you've seen this all before. But the point here, right? This rectangle is a simple geometry, right? When I write down a Stokes-Ohm equation, now I have a partial differential equation, and partial differential equations worry about boundary conditions. In other words, they care a lot about the geometry of my device. So if I start making this kind of geometry with these funny lobes, so this was done by Eli Zeldov and friends in this Nature paper. So here's my boring conductor of gold. You see the flow just kind of goes from bottom to top here, right? But if I have a hydrodynamic device, I'll see vortices, right? I'll see, it's kind of like when I go to the river, I look at some of the corners of the river, there's going to be some local eddy currents that just kind of swirl and are stuck. And we can see that happening exactly in some of these hydrodynamic devices. They're doing some squid on tip to actually locally image and see these current flow patterns. So that's kind of the most straightforward example of how hydrodynamic transport is new and different. Right? You see these vortices. If you want to be fancy, you can call that a topological effect of vortex is some topological object, whatever. But in general, in electron transport, you build up this whole lore of how you interpret data, right? There's like temperature dependencies and all this stuff. But if you start including interactions in this hydrodynamic way, we kind of have to go back and revisit a lot of these statements that are actually no longer really true. So here's a bunch of examples of so the top few are experiments that have been done. So for example, superballistic flow, there's this very famous statement that I mentioned earlier of, if you make a device super clean, you have E squared over H conductance. That's the best conductance you can ever get. Turns out if you turn on interactions, you can get conductances that are higher than E squared over H, right? Because that E squared over H was a non-interacting statement. So people have measured that. There's a famous Wiedemann-Franz law, which says that the ratio of thermal conductivity to electrical conductivity is constant. It's strongly violated in hydrodynamic devices. This Corbino field expulsion basically says that I have a current flow with no local electric field. There's this Gurgy effect, which, so normally, and this is kind of a funny quirk of electron transport, you call something a metal if its conductivity, its resistance increases as a function of temperature. But if you have this hydrodynamic device, which is in some sense the cleanest metal you could possibly make with interactions, it turns out that the resistance actually decreases as a function of temperature like an insulator. So that kind of statement is kind of just wrong. And then there's like, in the talk last week, they kind of, Chimao kind of mentioned things about strange metal, linear T resistivity, and people have proposed that hydrodynamics might be a way to think about some of these strange metal physics in, say, the cuprates or heavy fermion materials. Okay. So all this to say, hydrodynamics has been very interesting. Lots of experiments have been done in the past 10 years or so. Now I want to go kind of switch gears, right? So that's our character number one, electron hydrodynamics. And now I want to ask, what happens to fluctuations and noise in a hydrodynamic system? And before I properly define all of that stuff, I want to ask, you should care about noise, and in particular what I'm calling noise thermometry. So what this name suggests is that I measure something called noise, or current noise, and I'm going to use it to measure temperatures. Okay. So one thing you can do with this technique, for instance, is to do bolometry, which is the measurement of electromagnetic radiation. So people can use this technique to measure in these papers by Efetov and all, they can measure the arrival of single photon events. Right? That's how sensitive some of these techniques can be. For those of you who are more, astro inclined, you could make the argument that the first noise thermometer ever made was a Dickey radiometer, right, to measure the cosmic microwave background. So this is, kind of extension of that kind of technique. Okay. So perhaps more pertinent for me as a condensed matter physicist, I care a lot about properties in materials, right? And you can use this noise thermometry technique to make measurements of thermal conductivity. So for 2D materials, it turns out this is a very challenging problem. And the reason it's challenging is because the coupling between electrons and phonons are weak. But if you think about how does a regular thermometer work, you usually take some thermometer and you need to touch it against the material, and the phonons thermalize, right? But if I care about the electronic part of the temperature, right, that electronic temperature bath could actually be very disequilibrated with the phonon temperature. So you need another technique to measure kind of electronic thermal properties. Noise thermometry gives you a direct access to that piece. So in particular for graphene, it's pretty nice. So this is actually this famous experiment by Philip Kim's group, when they measured this Wiedemann-Franz violations, measured the thermal conductivity, was essentially done by this noise thermometry technique. And well, a long story short, they had issues in interpreting this data because they assumed that the model to interpret this data was they assumed it's a boring ohmic conductor, and then they're claiming it's hydrodynamic. But really what you should be doing is you need to develop a hydrodynamic theory of this current noise to make a statement about this Wiedemann-Franz violation. But kind of more pertinent and kind of on a more positive outlook, I want to ask the question, right? You put in all this work, right? Let's make devices cleaner and cleaner and cleaner over 100 years, and for what, right? And I want to argue that if we make noise thermometers with these hydrodynamic devices, you actually get an improvement in the sensitivity by a dramatic factor. Okay, so with that kind of prelude to noise thermometry, let me give you a quick rundown of how this technique works and perhaps why you should care. So let's imagine we have some conductor, right? I'm going to hold it at a finite temperature, right? So this is just some metal, I have some electrons in it, and I'm going to connect up some ammeter to it. Note there is no battery at all connected to this. So of course, the average current going through this ammeter is 0, right? It's in equilibrium, nothing is happening. The important point, however, is that even though the average current is 0, if I measure this 2-point correlator, this fluctuation, so this is what we call the noise, so I of t and I of t prime, this is actually not 0. And that's because, well, these particles are undergoing white noise fluctuations. The temperature is oscillating and jiggling these electrons around. So you get an RMS speed here that gets converted into an RMS current, essentially. This is very famously known as the Johnson-Nyquist theorem or the fluctuation dissipation theorem. Right? So on the right here, you have this 2 kBt, T naught the equilibrium temperature, divided by the resistance. Okay, so you can take this result and then massage it. So you write this S, take the Fourier transform, write this S in terms of units of temperature, so you multiply by these factors. We call that the Johnson noise temperature, right? It's just the noise and temperature units. And this is exactly equal to the equilibrium temperature. So the point here that was made by Johnson and Nyquist is that if I measure the current noise, I get a direct access and direct measurement of the electron temperature. This, as opposed to, say, a liquid mercury thermometer or something like that, this does not require calibration at all, right? At least in a theoretical sense. I don't have to set a 0 being frozen water and a 100 being boiling water. In some sense, this is the fundamental definition of temperature, right? If you like, 1/2 mv squared is you can define that as being related to the kBt, right, from thermodynamics. So I can't help but mention this fact that, of course, because we're talking about fluctuation dissipation, Einstein thought about this back in 1906, of course, right? The fact that one of his many famous works was proving that molecules actually exist, right, through Brownian motion. But he actually thought about this problem and then said it's not measurable, so he just gave up. And I guess he just left it for Johnson and Nyquist to get the glory 20 years later. Okay. So this story is great, right? If you want to make a thermometer, you want to measure the cosmic microwave background, or just to make some temperature sensor in some spacecraft, fine. But if I want to do thermal transport measurements, like measure thermal conductivity, that's a non-equilibrium process in the sense that I need to apply some temperature gradients, right? It's no longer equilibrium. So I need to generalize this, this result beyond equilibrium. Okay. So let's kind of revisit this problem again, right? So now we are attaching a battery to this, and so which means that when I apply a battery, the system is going to heat, right? So here's something what the temperature profile might look like. You have a hot spot in the center, and it's colder at the contacts because you're holding, the metals are good conductors, and it's just held at some temperature. Okay, so you heat the system, right? There's more temperature, more energy, there's more fluctuations. The noise will increase. You can measure that. And now, in order to say something about the thermal conductivity, so that's step 3 here, the experimentalist needs to kind of model this device, do a lot of math, and kind of like try to connect this noise increase to my thermal conductivity. So this was done, starting from, say, like Prober et al. In 93. There's a paper by Sir Carl Calvin Loss, whatever, in 2000. And you take the normal assumptions. You assume that it's a metal, meaning you assume that you have ohmic equation of motion, you have Wiedemann-Franz law, right? Solve all this thing, right? Okay, but kind of at a higher level, what you're really doing is you're saying, okay, when I measure this Johnson noise, it's some object with temperature units. But the temperature is now some field, there's some distribution of temperature. And so what this Johnson noise is measuring is kind of some average of the temperature, so to speak. I need to condense it down to one number. So this is the form that you get at the end of the day. So as a pretty simple form, it's input power, 2-terminal resistance, Wiedemann-Franz ratio, electron temperature, and some universal 1/12 prefactor. And the surprising thing about this result is that this result actually doesn't care about what geometry you use. So if you look at the square versus this funny blob conductor, right? This result works once I set the resistance, this result works for both geometries, any geometry you want. This is essentially just a funny fact of the fact that the Ohm's law can be written in a Poisson equation, or Laplace equation, and thermal conductivity is also a Poisson equation. But anyways, so you get this funny geometry dependence for this ohmic case. But if you think about what happens for, if I want to do this all for a hydrodynamic model, I want to, change the ohmic equation of motion, then you start scratching your head a little bit because, I argued earlier that hydrodynamics is a PDE. It depends on geometry and stuff. So it's clearly something has to happen to this, and it's not correct to apply this for a hydrodynamic device. So we need to go back and fix that. Okay. The second thing is that, well, I argued earlier in a previous slide that this Wiedemann-Franz ratio, this ratio between thermal conductivity and electroconductivity, can be dramatically modified in the presence of hydrodynamics. Right? So maybe one thing you can do is you replace this Wiedemann-Franz ratio with the Wiedemann-Franz ratio corresponding to hydrodynamics. And there's a general statement that, at least in the simplest hydrodynamic models, L goes down. Roughly speaking, you can kind of hand wave this as follows. If I turn on interactions between electrons, electron-electron scattering conserves momentum. Because it conserves momentum, it doesn't really change conductivity. But it does change the thermal conductivity. So in general, it'll decrease the thermal conductivity, so L goes down. Now, if L not goes down, right, and I keep all the other things on the right-hand side fixed here, like the input power and the resistance and so forth, that means delta TJN goes up, right? And if you're measuring it as an experimentalist, it's good to have large signal, right? So which would imply that I have larger noise sensitivity for these devices. Okay, right, so good. So okay, so now we need to actually go through and kind of do all of this calculation, right? Right. We first need to determine what the temperature profile is from heating the device, and then we need to figure out this averaging step to get the Johnson noise temperature out. Okay, so let's start with the first part and show. Let's see how what the difference is between this ohmic and the viscous case. So, you solve some heat equation, fine. right? And well, in the ohmic case, heating is just I squared R heating. So in local coordinates, or like a local field, it's just gamma times U squared. Right? That's I squared R. And you get, essentially, for this kind of flow profile, it's just uniform everywhere in the sample. You solve the heat equation, you get some parabola. And for rectangular geometry, it's just always a parabola. It's kind of boring. Now, if I do the same thing on the viscous side, heating does not proceed by I squared R heating, right? If I have a fluid flowing in free space, I don't care how fast that fluid is moving. It doesn't heat because of translational symmetry, right? A fluid only heats if there are velocity gradients. If one layer of fluid moves faster than the other, that's what triggers viscosity. And so that's what's reflected here. Essentially, the heating is proportional to the stress tensor squared, or gradient of velocity squared, right? And as a result, for this Poisson flow, the heating ends up being concentrated in the boundary where the derivatives of U are the largest. You can kind of think of this in the following way. If I have a fluid flowing in a pipe, or hydrodynamic electrons flowing in this rectangle, what's happening is the boundary here is actually rough. So the electrons eventually hit the boundary, and that's when they lose their momentum, and that's where they end up heating. That's why the heating ends up being close to the boundary. Okay, so then you solve this heat equation in multiple geometries, right? So here's aspect ratio 1/40. So this is a really skinny quasi 1D device. And you see that it's kind of boring. Everything's squashed in the y direction. There's no variation. This picture more or less looks like that picture. It's basically parabolic. Now, let me fatten up the device. So now it's aspect ratio 1/1. So it's no longer quasi 1D. Right? Now you really see that, okay, here's some heating peaks at the top and the bottom, and it's actually colder in the center. Right? And then it has some variation along the x direction. I should mention that the contacts are on the left and the right here. So current's flowing from, say, left to right. Right? So now the temperature profiles are very geometry dependent. And if we want to average this temperature profile to get some Johnson noise, it's sensitively going to depend on geometry. So there's an effect there, for sure. Okay, so you make these temperature profiles, and then we need to figure out how to average this temperature and determine the noise. So I want to bring us, again, back to, say, the 1930s and ask really, this theorem should be on E&M 101, right? So the question that Shockley and Rambo asked, this is back in the 1930s. They're thinking about, free electrons, electron guns, shooting them through free space. You have some gigantic conductors. And so they asked this question. If I have this electron in the center moving to the right with some velocity, and here's some gigantic parallel plates, what is the current in the ammeter? So my postdoc advisor, Brian Skinner, was the one who told me about this problem, and he heard it from Leonid Levitov. But anyways, so I, being a very naive student, I guess, I said, well, what does an ammeter do? It measures the electrons as it passes through. The electron's always over here, ammeter's down here. Current has to be 0, right? And well, of course, Maxwell would be rolling in his grave because he spent his life telling us that electric field physics is highly non-local, right? This electron pulls surface charges onto the surface of the conductor, and so if I move the electron, I move the surface charges, and this moves charge through the ammeter. This leads to a net current, right? If you like, this is exactly what happens when you talk about capacitors and the displacement current through there, just formulated in a different way. So the genius of Shockley and Rambo was that they actually have a very simple equation for what the amount of current you should get is. So that's just electric charge times velocity times this so-called effective potential, which is what you get if you hold, say, the left plate at unit voltage and the right at 0. Okay. Right. So, so why do I care about this when it comes to noise? Well, I want to start oscillating an electron in the center, right? And I want to measure the oscillations in the ammeter outside. So the Shockley-Rambo theorem is a very important piece of the physics here. Okay. Now, if you're familiar with actual materials, there's no such thing as a non-local electric field. Everything gets screened by electrons. If this is a metal, right, any electric field will pull all of its neighbors, and you don't get this plate effect anymore. So, and I like to self-soothe myself by stating this to myself, right? I'm not actually that bad at E&M. So we need to play the same game again, right? What happens if I drag this electron in a conductor and say, what is the current in the ammeter? It turns out this, even though technically there's no surface charges being dragged onto the plates of the metal, right? There's still a non-local effect, right? The charge screening is still non-local. Basically, if I drag the center charge, the screening will drag all of its electronic neighbors as well, and this is non-local. So it pulls all of those charges along, and this again leads to a net current, right? So you can think of this charge screening as a result of current conservation in my device. Well, now it's not in free space. You have a conductor sitting around here, so you actually have to model this conductor. And so what Song and Levatov did was they treated the case of an ohmic conductor, and it turns out that maybe by a little bit of magic, you just end up getting the exact same result as Shockley and Rambo. That connection is maybe not so obvious and not so trivial, but it's true, right? And so specifically for the rectangle, you can kind of think of if I have some velocity field of these electrons that I'm dragging, the total current in here is something like the average of the velocity field over the rectangle. Okay, so I mean, there's not much magic to this. Okay, now if I want to talk about hydrodynamics, I need to put in this viscosity term. Turns out that this is quite non-trivial, maybe I'll talk about later, but specifically for the rectangle, you get the same result. Later, I'll change geometries, and this will be not the same result, but for now, I'll just keep it here. But so this is important because I want to, so now I want to go and actually measure the noise, or compute the noise for my device. So how do you do this? Well, you flip Oven, Landau, and Lifshitz because of course they did everything, and they tell you to write down this disgusting-looking equation of motion. But actually, this is not. If I take a step back and look at the structure of this equation, well, this is actually just the Stokes-Ohm equation, right? What basically the statement is that the fluctuations in my system obey the exact same equation of motion as if I drove it regularly. The difference is that now I'm allowed to input this force in, this thermal force or thermal kick, right? Because I need the temperature to kind of kick these fluctuations along. If you like, this is some version of a Langevin equation. Okay, so you go ahead and solve this, right? Some nasty PDE for this object, which looks like the current squared that I want. You notice the annoying fact that one of these does not look like the other. This has a subscript u sub s, the other has x. This is essentially technically where the Shockley-Rambo theorem comes in to convert this u sub s into the u of x. That becomes some current, that becomes some TJN. Right, fine, right? You do all this math. But to take a step back from this, the point I want to make is that you solve this equation of motion. What's the difference between the hydrodynamic and the non-hydrodynamic case? It's the presence of this viscosity. What this viscosity is doing is quantitatively modifying your temperature averaging procedure, right? So, to summarize, you compute some temperature profile that's going to be modified by hydrodynamics. Then you're going to compute the solution to the noise equation that's also modified by hydrodynamics, right? And you summarize all of that in this equation that I've written down here, right? So there's two main changes to the ohmic result that I said before, right? So if I ignore this f, if I set f to 1, this is basically what I said earlier is the ohmic result, with the correction that you need to put in the generic Lorentz ratio instead of the usual Wiedemann-Franz ratio. And then there's going to be some hydrodynamic correction, which depends on the various length scales of the problem. right? So, okay, so there's, you can plot this and see what it looks like, right? At the bottom, so Gaussian, this is Gaussian length against aspect ratio. At the bottom here, this is where it's ohmic. You recover f equals 1 as you expect. On the left here is when the system is thin. So the temperature profile looks like a parabola. Again, it looks like f equals 1. You get f equals 1 here because this parabola looks like that parabola. So if you want something non-trivial, you go up to the deep blue region where you have funny-looking temperature profiles. And well, it turns out the worst damage you can do is 3/5. And so if you ignore this term for rectangular geometries, as Philip did, lo and behold, it actually turns out to mean, okay, well, I'm a condensed matter physicist. 40% error is not so bad, considering their violations are orders of magnitude, okay? Right. Of course, if you want to be more precise, depending on who you ask, 40% is pretty bad. Anyways, the point is here, so this f, at least for a rectangle, is some slow order 1 function, doesn't vary too much. So when we come back to this argument that if we make low Lorentz ratio, this is the thing that's actually dominating the change in these hydrodynamic devices, you can actually make ultra high sensitivity noise thermometers if you do this. Yeah. So, right. So that's kind of like a engineering proposal, if you will, to go and make graphene or whatever your favorite hydrodynamic material and use it for this task of noise measurement. It'll be very, very good. So if this is down by a factor of 10, that means your signal goes up by a factor of 10, right? Okay. Right. So with that, let me go into kind of the second part and perhaps what was the confusing part and why Philip came to ask Brian and me, among other people, to start thinking about this problem. So of course, the rectangle is a simple geometry. What's the next simplest geometry you can think of? Well, it's this annular Corbino geometry where you have a contact on the inside and a contact on the outside. You have circular symmetry. It's great. It has every boundary is touched by a contact as opposed to the rectangular case. That's great for a lot of transport things. Of course, I'm not an experimentalist, but I can imagine making this kind of device might be somewhat of a nightmare for some students because now you have to put your wires vertically on top of the contact in some way and not have it electrically. Anyways, right. So this is fine for regular ohmic devices, but it turns out that when you make the system hydrodynamic, everybody who has worked in this field, who has looked at the Corbino, has struggled in one form or another dealing with some of the subtleties of the Corbino problem. And I'll kind of explain a little bit what I mean by that. So here's essentially Philip's version of this problem in his experiment. So he made 2 measurements of this graphene device. Right? He measured the electrical resistance as a function of magnetic field, and then the thermal magnetoresistance, or really the current noise, as a function of magnetic field. Right? And so here's what he gets as a function of temperature. Right? So from low temperatures to high temperatures, 15 to 200 Kelvin in both cases. On the left-hand side, you see that you just get nice parabolas. Okay, and this is precisely what you normally expect. Right? Loosely speaking, why does the resistance go up as you increase magnetic field? Well, if I have an electron going from point A to point B at 0 magnetic field, if I start turning on the magnetic field, the paths curve. Right? So if I try to go from point A to point B, the effective path length of this electron gets longer, hits more impurities, and so there's more resistance, right? So, that's what you normally expect. But this argument is supposed to also work for thermal magnetoresistance. There's no real difference, at least from a Wiedemann and Franz perspective, between this electrical and thermal. So this, in principle, should also work here. But this picture doesn't look the same as that one. Not only does it not look the same, it actually goes down, right? And if you have sign changes, that's usually a sign that something is terribly wrong or qualitatively different. Something strange is happening, right? So what this is telling us is that the thermal conductance is increasing as a function of magnetic field, and that's very strange, right? So So this actually only happens at elevated temperatures, so around 120 to 200 Kelvin. This is exactly the regime where you expect to see electron hydrodynamics. So they thought, oh, maybe this is some kind of hydrodynamic effect. Okay? So maybe it's like, something like viscosity goes down with temperature, so maybe it's something like that. But they went to all their theorist friends, asked everybody, and everybody basically agreed. If you compute the thermal conductivity in the hydrodynamic regime, thermal conductance should still decrease as a function of magnetic field. Interactions won't change that fact, essentially because this argument still holds. So they came and asked us, and well, instead of going here and asking this question, we said, okay, well, you're actually interpreting your result using this formula, which is ohmic, and we're just like, why are you doing that? We just published a paper saying you shouldn't do this. Of course, so you ask, there's really an F correction on top of this, and well, we need to go back and compute this and see if this actually does the thing that you want it to do. Okay, so you run through this same game again, and do all of this now with a slightly different geometry. So let me just show you the results. Right, so for the temperature profile, this is the ohmic case. So these are all normalized by input power. So here you see 0 magnetic field. The field lines go out. Right, you put out a magnetic field. The current flow starts spiraling. But actually, if you normalize by power, these two pictures look exactly the same. So the temperature profiles look exactly the same. This is more or less why in an ohmic device, nothing interesting happens. Okay. Now let's do the same thing for a hydrodynamic and viscous device. Right. So again, when you turn on magnetic field, you start swirling your current flow lines. And the important point is that the heating depends on gradients of velocity, not the magnitude of velocity. So what happens here? So at the boundaries, the current is forced to come out at right angles to the boundary, and then they're twisted kind of violently by the magnetic field. So that's why you see that in the center and on the edge, it's higher heating. But somewhere in the center, you see this dark ring, right? That's where the heating is lower. Essentially, the current flow lines have more flexibility to try to be more parallel, and so they heat less. And then you take this and you solve this, right? You see that the temperature here is kind of lower and much more blurred out. In some sense, you get lower temperature as a result of this kind of heating. You can schematically kind of think of this fact as, well, heating is kind of being pushed towards the boundaries, and because now the heating is being pushed towards the boundaries, the heat can escape through my contacts easier, leads to less effective heating. So just to make line cuts, because that'll make it easier to quantitatively see. So here on the left, you see that at some point, at this blue curve is the magnetic field. With magnetic field, it dips. There's some minimum in the center. And then here, so the red curve is the one with magnetic field, and the blue, without magnetic field, and the blue curve is the one with magnetic field. You kind of see that the peak temperature is lower. Right? So in a hydrodynamic device, the temperature, if you normalize against input power, goes down. There's less heating, right? And if there's less heating, there's going to be less noise. Okay, so now you need to go and do this stuff. Let me go a little bit quickly through this. So you do run the same game again. You need to solve Shockley-Rameau and this geometry, and then you need to solve this noise equation of motion. And you run into something known as the Corbino paradox. Well, at least Brian and I like to call that. I don't know if other people call this yet, but it's kind of fun. So what you need to do is you need to solve the Stokes equations in a Corbino geometry. Okay? One fun fact about this circular geometry is that you don't need the equation of motion for the current to know what the current flow is. That's actually given to you just from current conservation and rotational symmetry. So divergence of u being 0, that's current conservation. That means the radial current has to be I over 2 pi r. Simple enough. So what does the equation of motion actually tell you? Well, it tells you what the electric field is locally. And well, if this is 1 over r, you remember that 1 over r is a harmonic function. you take the Laplacian of a harmonic function. By definition, that's 0. So I put this in, that's 0. That means the electric field is 0. Well, that's strange. I have current flow. I have net current flow with 0 voltage locally. There's zero electric field. Does that mean I have a superconductor, right? What is going on here, right? Okay, so maybe you do your normal physicist thing and you're just like, fine, right? Like maybe I just didn't model it appropriately. I just add in some like fudge impurity factor to like, fix this up. Unfortunately, the problem is not that simple. And that's the fact that I just told you that this device heats, and this heating depends on the current. So what the heck is going on, right? I have flow with no voltage drop, with no electric field, and the device is heating. And so I can't be violating energy conservation. That, even as a theorist, that's too much, right? So what is going on? The point that I want to make here is that, especially for those of us who work in electron transport, we're just used to J equals sigma E, which is a local theory, right? It's not a PDE, right? It only cares about a local space point. But hydrodynamics is non-local. What's going on is that essentially the boundary, right? When I attach a battery to this thing, the boundary has to provide energy into the system, right? And so if you work this out properly, so this was done by Grisha-Falkovich first in 2019, is that even though you don't have electric field in the bulk of this device, I need to model the boundary when I put on these contacts. And if you do that, what you get is that you get these sharp contact voltage drops on the edge, right? And so if you include this boundary effect, this voltage drop here is what's giving rise to so supplying the energy for this flow. Loosely speaking, you can kind of think of this in the following way. If I have some radially outward flow, there is some viscous stress energy stored in the flow because it's expanding. But then when that flow goes into the contact, there's no more viscosity. So all that viscous stress energy has to go somewhere, and under these assumptions, it goes into the potential energy, right? So to conserve energy. That's why you get a sharp jump at the interface between these two materials. Okay, and just to emphasize that this is not something that theorists just cook up to solve issues related to conservation of energy, and I'm just not trying to make some toy argument to cover my butt. Here's an experiment that actually measured this effect. So this is by Shahalani in 2021 in a graphene Corbino hydrodynamic device where they see exactly this, the fact that the potential drop, the electric field in the bulk of the sample is 0. And then you see some sharp contact drops at the edge. Okay. Right, so funnily enough, this electric field being 0 in the bulk is not wrong. It's actually a feature of hydrodynamics. And if you're interested, I can explain more about why that is later. But essentially, it's because you have more or less a translationally invariant fluid. Okay, so let me just shortcut this a little bit. So basically, you need to go back and solve Shockley-Ramo, and I spent lots of sleepless nights trying to figure out this problem because I didn't actually understand how this problem was set up. The first paper we wrote on this, I actually did it wrong, but I ended up guessing the right answer for the rectangle. So that had to go, and then I was worrying for a long time that this PRL that I had was actually wrong. And until I actually solved, I eventually figured this out, and I solved all the equations. It's like, oh, thank goodness. It's actually, my assumption was actually correct. But yeah, so you need to set up this Shockley-Ramo problem, fine. And we solved this issue of Corbino paradox. Okay, so let me just fast forward to the results. So again, we have these temperature profiles, right? The temperature profile is lower in a viscous case when you turn on magnetic field. If I plot this correction F as a function of magnetic field, so it's always 1 in the ohmic limit as you expect. And then in the viscous limit, when you start having this hydrodynamic stuff, it decreases as a function of magnetic field. And this is exactly what like Philip and friends were seeing. This drop, and qualitatively, at least, we have this effect. And you can go through and, well, we want to be quantitative about this stuff. You do a lot of work fitting this model to their actual data. So here's the electrical magnetoresistance and the noise power, and here's the data and the parabolas or the fits. It's actually pretty non-trivial because it's a multi-parameter, multi-dimensional fit against this essentially numerically evaluated function. You can back out the Lorentz ratio. So after doing all of this, you see that the Lorentz ratio is actually suppressed as you expect for this device, which is great news because I do all this work and I have no guarantee that any of this even fits or works for the material, and everything seems to work out well. And then you can also use this to back out viscosity. And in general, the value of the viscosity, is at a reasonable range compared to completely orthogonal techniques that people have to measure viscosity. Just as a brief comment, viscosity in a classical fluid, I guess, is relatively easy to measure. In an electron system, it's very hard. So even adding one orthogonal technique to verify the viscosity is very interesting. We'd like to develop better ways of pinning down this point, but this is a new way of doing it, which is pretty cool, using this noise thermometry. So with that, let me just throw up this conclusion slide and just emphasize that there's a lot of work doing electron hydrodynamics, and we have this new angle on thermal noise to, maybe we can use these things as very good thermometers, and we can use them to measure interesting parameters of interest in devices. I should emphasize that, in general, there are many other things you can do with noise, right? Shot noise being a very famous one, but generally looking at some of these non-equilibrium observables can tell you a lot about systems that maybe traditionally we're not so used to thinking about. So I really would encourage all of you to think beyond our normal, say, Kubo formula biases. With that, I'm happy to take any more questions.
Okay, thank you, Aaron, for a very nice talk. Do we have questions for Aaron? Yes, okay.
Oh, thanks.
So have people looked at adding a magnetic field, not in the Corbino geometry, but in the Hall bar? Because I know, like for the electron transport, you pick up, if you had a magnetic field, you get like an off-diagonal term in the viscosity. And
yeah.
People have looked at the electron transport, but what does that do with thermal transport?
Okay, let me put it this way. Thermal transport in graphene is a very complicated problem. That's why Philip and his team are trying to develop this. Essentially, they're the ones pushing the frontier of noise thermometry in order to make a thermal measurement. I mean, there are other techniques that people do, but generally it's, the data you get is, as I understand, not so great. So thermal transport is generally much, much, much harder than electron transport. So probably has not been done. As you mentioned, people have looked, so there's something called Hall viscosity, that's the analog of Hall conductance. There's predictions that it should be quantized and so forth. Turns out to be hard to measure in experiment. There is one 2019 experiment by Berg-Uden who measured the Hall viscosity in anything in Hall bar geometry. So people are working in that direction, but generally it's a lot of these features are hard to disentangle because if you're familiar with viscosity as a tensor, it's a 4-component tensor, right? So that's 16 components. Okay, you might reduce it by symmetry and so forth, but getting that is from experiments is generally hard.
All right, other questions for Aaron? Maybe one more question? Yes, always on the opposite side. Very good.
Okay, Thank you, Aaron. I like the talk very much. And I would like to ask, so when the electron-electron interaction is so strong, then the electrons might pair up into Cooper pairs. This would change the picture of the hydrodynamic thing, right?
Yeah. So yeah, good. So the assumption here, right? So whenever you say something is strong, the question you always need to ask is compared to what, right? So what I mean here when the electron-electron interaction is strong, it's strong compared to the impurity scattering and strong compared to, say, the scattering, electron-electron scattering like this, strong compared to the sample dimensions, right? Implicitly, what I'm assuming here is that it's weaker than any, say, Cooper pairing or whatever that would reorganize my quasi-particles into something else. So in some sense, this is a weakly interacting Fermi liquid, if you like. So you can think like liquid helium. This is more or less liquid helium-3 in a metal, right? In a certain sense.
All right, let's thank Aaron again. If anyone else has questions, please come see